Today we will be looking at Chapter 3, Soil Physical Properties. Physical properties control how air and water move, how roots explore, and how workable the soil is. We'll examine texture, structure, pore space, bulk density, consistency, and color. Then we will connect these traits to erosion risk, compaction, irrigation, and traffic timing. Understanding these links is essential for making good agronomic decisions. Mineral soils typically have about half solid particles and half pore space when in good condition. Pores are filled with varying proportions of water and air depending on recent weather and drainage. Management aims to maintain a balanced pore network that supports roots and microbes. Organic matter and stable aggregates are central to achieving that balance. This figure comes from your textbook and looks at the approximate proportions of various phases by volume in a moist soil surface. Sand, silt, and clay are defined by particle size, and each behaves differently. Proportions of these separates determines the texture class of the soil textural triangle. Knowing the class lets you predict water retention, nutrient holding, and the ease of tillage. It is a foundational diagnostic tool in soil science. It has large particles and large pores, which drains and aerates quickly. However, it holds little water and few nutrients, so fertility can be harder to maintain. Sands are less prone to compaction, but can be droughtly without organic matter. Adding residues and mulches helps improve water and nutrient retention in sandy soils. Silt feels smooth and is excellent for water retention, but it is highly erodible if left bare. Silty surfaces can crust after intense rain, reducing infiltration and emergence. Residue cover and living roots are crucial to protect silty soil. Conservation tillage and cover crops can make a large difference in performance. Particles are tiny, with a huge surface area, yielding high water and nutrient holding. They drain slowly and can become oxygen limited if compacted or waterlogged. Working clays, when too wet, causes smearing and long-lasting structural damage. Timing traffic and building on organic matter is the key to a healthy clay field. Figure comes from your textbook and shows the same mass of a mineral has a much greater surface area when it is pulverized. The layered clay crystal is similar in nature to a stack of thin sheets of dough. Texture changes only very slowly at the field scale and is essentially permanent for management purposes. Trying to add sand to clay at scale is impractical and often counterproductive. Instead, we modify management, traffic timing, residue, and irrigation to fix the texture. Recognizing texture early can save years of trial and error. Textural triangle shows the limits of sand, silt, and clay contexts of various texture classes. Field method uses ribbon length and tactical cues to estimate clay, silt, and sand. Laboratory methods like hydrometers or pipettes provide precise percentages for classifications. Once you estimate the trio, use the textural triangle to name the class. Practice improves accuracy and helps with quick field decisions. Structure describes how primary particles are arranged into aggregates and pore networks. Good structures improve infiltration, gas exchange, and root penetration. Poor or destroyed structures lead to crusting, sealings, and runoff. Biology, organic matter, and gentle management build and protect a structure over time. Soil structure units are classified according to shape and size. Granular aggregates are small, rounded peats common in topsoil with roots and organic inputs. They support rapid infiltration and high biological activity. Practices that maintain cover and living roots favor granular structure. Minimizing aggressive tillage protects these fragile crumbs from collapsing. These structures feature thin horizontal plates that impede vertical flow and root growth. It often forms from compaction, heavy traffic, or repeated freeze-thaw of saturated surfaces. Correcting it requires traffic loads and restoring biological activity. Over time, organic additions and root growth can reopen vertical pathways. Blocky peats have roughly equal dimensional shapes and are common in clayey subsoils. Angular blocks have sharp faces, while subangular blockies are more rounded. Moderate blocky surfaces can move water reasonably well if pores are connected. Excessive compaction converts it into massive, while severely restricting plants and roots. Volcanic structures have vertical columns with flat tops, often in subsoils with shrink-well clays. Columnar have rounded tops and is commonly associated with a sodium-affected condition. Both can impede lateral root growth and will slow infiltration unless fractures are present. Sodic soils often require chemical amendments and improved drainage to restructure. Columnar are often associated with a higher sodium soil, and there is poor water infiltration and root penetration. Stable aggregates protect against erosion by reducing splash and runoff. They create a range of pore sizes, storing water while still providing aeration. Aggregates also make soils easier to till within the right moisture window. Keeping soil covered and biologically active is the fastest route to stability. Soil without humus becomes cloddy, which is focused on the left, whereas humus-rich soil is granular, which is seen on the right. Soil porosity is the fraction of soil volume that is pore space, while bulk density is mass per unit volume. High bulk density usually means fewer or smaller pores and harder root penetration. Tracking bulk density over time flags compaction or improvement from organic inputs. Aim for a structure that balances macropores and micropores for your crop and climate. When rocks weather, they become loosened and less dense as soil is formed. The zone of compaction has a higher bulk density and a lower permeability. Macropores drain quickly and allow oxygen to diffuse into the profile. Micropores hold water against gravity and supply plants between rains and irrigation. A functional soil needs both, created by structure, roots, and fauna. Tillage may create temporary macropores, but biology sustains them in the long term. Consistency describes resistance to deformation and rupture at different moisture states. We look for moist, friable conditions to minimize damage during tillage or traffic. Too wet and soils smear. Too dry and they shatter into clods. Learning the feel will save fuel, time, and structure. Darker colors usually indicate organic matter is enriched near the surface. Red or brown hues point to an iron oxide and great aeration in the past. A gray or bluish color indicates a prolonged saturation and reduction. Color patterns help diagnose drainage class and seasonable water tables. The Munsell system standardized hue, or dominant color, value, or lightness, and chroma, or intensity. Field charts allow consistent descriptions between observers and sites. Consistent color calls for the support of soil classification and drainage interpretations, learning to match tips quickly, and recording the full notion.